Okay, kids, here we go. We got some equations to do. You know, this is physics, right? And all this stuff that we've been doing so far with waves has been all like this theory stuff. We haven't really done any math. I mean, we have talked about one of the equations. That's muy importante grande. And you will need that this week to do some calculations. Velocity of a wave equal frequency times wavelength. We've talked about it. We haven't done anything with it. And remember that frequency, this is one of the wave rules. Remember wave rules. One of the wave rules is frequency of a sound source doesn't change. Okay, that just keeps putting out the sound. But the only thing that you can change velocity, you can change the wavelength. That's one point I tried to make in the last week when we were going over that lab sheet. So this is our first equation. But I'm not actually going to be interested in this one today. Nope. We're going to move past this bad Larry here and go into simple harmonic motions equations. Now, if you're a note person, which I hope you are, if we go back to the sweet wave outline right here at the top, this is what I'm going to be focusing on today. The other day in class, I skipped that. I said, we'll come back to that. Well, guess what time it is? Back to that time. So let's do simple harmonic motion. And remember, that just means repeat it over and over again, the same path, back and forth, simple harmonic motion equations. Okay, so there are two of them. There are two of them that you need to know. Dos el grande. Okay, we need to know these two. One of them is t is equal to 2 pi square root L over G. That's an L. I know, look at an L. It's kind of nasty. I'll fix that. That does look kind of nasty. It's a cursive L. There we go. So this is called the pendulum equation. This is for pendulums. And now a pendulum is anything that has anything that goes back and forth. You're getting very serious with the mass on it, and the mass is called a bob, and that goes back and forth and back and forth. Pendulum. You know what a pendulum is. Clocks have pendulums. Back in the day, that's how they used to keep time with pendulums. Yeah. Okay. So now this equation has variables in it called t for this is time period. That's how long it takes to do an oscillation. An oscillation for a pendulum is out and back. Okay, how long it takes to do that. That's that time period. Time period. 2 pi is 2 pi. L is the length of the pendulum. And little g is gravity, gravitational acceleration. Okay, on Earth, we all know. 9.8. So that is our pendulum equation. Then we also have, well, actually, let's keep this one up here. I'll just erase some of this stuff here. We also have an oscillation. This is for oscillations of a pendulum. We also have oscillations of a spring. So something on a spring, whether or not it's like this, which is a little more complicated because you've got gravity involved, or horizontally. I'm doggone it, you're going to watch the videos. AP Classroom, that is sign. You need to watch those. You do. Yeah, and not as fun as mine. Don't wear cool shirts like this in the videos, a person who's doing it. But they do a good job, and they use what's called a PhET simulation. And I'm not going to be putting PhET simulations up here in this video. I don't have that technology, okay? They do, so you want to watch those. It has some lab data, and they're really good. They're not too bad. They're only like 8 minutes long. You can do this. You can do it. And there's only a few of them, so you need to watch those. Trust me, AP loves this stuff. They do. They really love this stuff. I think disproportionately to how much the time this takes in the course, they love it. Okay, it takes this much time. They love it this much. So we got to know this stuff. Okay, so here is your other equation. So the other equation is still t, time period. And that's equal to 2 pi. Oh, it's the same equation. It's the same equation, right? No, you silly people. This time we're going to use m over k. Now let me grab the AP sheet for you kids. You relax. You've had a rough day, so you kids chill. Here we are. This is the one I broke. I was so excited when I was snapping it the other day. Let's see, where are mechanics? Here we go. Okay, so mechanics. Okay, here this stuff here. So we're on the mechanics. We go about yay far down this column. This column right in here is this harmonic motion stuff. So we have the time period and frequency, okay, of waves. Okay, they're inverse of one another. And then we have, there it is. There's the one I just put on the board, m over k. And then we also have L over G. They're right below each other. Okay, very similar looking. But those are simple harmonic motions for a pendulum and for a mass on a spring. A mass on a spring. How am I supposed to know this is a mass on a spring? Mass, spring constant. Okay, remember K, little K, spring constant. From Hooke's law. Remember that? Yeah. Remember Hooke's law? F is equal to K times X. Okay, yeah, Hooke's law, spring constant, PE and KE, 1/2 KX squared. Remember that stuff? Yes, so that comes back. Again, springs. AP loves them. Personally, I like fall better. I like fall, not spring. Springs, I like fall, but. So anyways, these are our two equations, and this is mass, this is the spring constant, and let's take a quick look at this. We know here that the length of a pendulum is going to have something to do with the time period of back and forth. Yeah, and sure as gravity. I mean, if you had very little gravity, okay, so if you have very small amount of gravity on the bottom or a big number on the bottom, okay, it's kind of inverse here, what's going to happen to time period. Okay, so if you had, well, there's a little bit of gravity, your time period, say you're on the planet Zork, which is this tiny little planet with very little gravity, you know, and your pendulum will take a long time to go back and forth because there's very little gravity pulling on it, so you have a long time period. Here, the length is clearly going to make a difference, and our course, our pendulum lab, will be coming up very shortly, is going to show that qualitatively and quantitatively. Here, we have a mass going back and forth, so like say you got a spring, and to it you attach a mass, maybe it's on a table, and and this is a wall or something, and you push the spring in, and then you let it go. Of course, if it has friction, it won't go for very long. It'll stop. But with no friction, we'll go back and forth, and this back and forth motion, this oscillatory motion, has something to do with the mass. Increase the mass, you increase the time period. That should make sense to you. If it's a heavier mass, it's going to take longer, heavy mass. Or if it's a light mass, heavy mass, take longer to go back and forth. Spring constant is going to matter. If you have a very large spring constant, okay, a large spring constant up here on the bottom is going to decrease your time period. Or if you have a small spring constant, it means easy to move it back and forth. Remember spring constant, it's how difficult or easy it is to stretch and compress a string, that K value. And the K value goes up. If you have a very large K value, it's very hard and difficult to stretch or compress a spring. So if we have a large number here, then we're going to have a large number here. Okay? Or a small number here. I just screwed that up. If you have a large number here and a small number here, if you have a large number here, you're going to have a large number here. Large, 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 small. Okay? Large, 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 small. Okay, so that's how those equations work. They're similar, but make sure that we understand which one works for what. This is a pendulum. You know, this is the length of a pendulum. This is the mass on a spring. Okay, I just wanted to touch the base on that and make sure that we have, where'd it go, oh, everything's everywhere now, what a mess, huh? So here I just wanted to make sure that we touch on this, and then now you can answer these questions. What effect would doubling the mass have on each? You know what, you think about those answers. Yeah, why don't you just give them to me? No, you think about it. Could you just think about it? Let that be a lesson to you. All right, I think we're pretty much done with this introduction to these equations. We're going to be using this one in our pendulum equation very soon, and we'll be using this one in lots of problemas grande coming up. All right, I think we're over and out on this. Now, after you're done watching this, go and watch the AP videos that were assigned. Now is the time to go watch those. Okay, do it now.